I'm now going over an example problem, which is a gas solubility in water problem. So our overarching equation that governs this is really what's called Henry's law. So it's the concentration of the gas in water equals this constant, which is Henry's gas constant in moles per liter atmosphere, which we find the constant for different gases in chapter 2 in one of the tables there. Okay, this is the partial pressure of the gas in air, which we might have a measurement of that. Okay, so what's going to be the concentration of gas in water? For example, oxygen in water or CO2 in water. Those are some things we want to know for environmental engineering problems. Okay, so it's important to know what are we talking about here when we talk about partial pressure. So the total pressure is 1 bar. Total pressure of air is 1 bar or 100 kilopascals or 1 atmosphere. Those are all equivalent, different units. For something like nitrogen in air, we know nitrogen is 78% of the composition of our atmosphere. That's 7.78 moles of nitrogen gas for every mole of air, which is the same as 78% of that, so 78 kilopascals. If we're talking about something like CO2, well, we know that in CO2, it's the partial pressure, right, of CO2. Right now, we're already over 400 parts per million. So we're at 413 ppm, which is the equivalent of 0.0413 kilopascals. Okay, so just some examples of different gases. Let's look at oxygen. So we're going to do a problem here, an example problem for oxygen. What's important is that the pressure of that gas is affected by altitude. So if we're taking an oxygen reading in water in a high mountain stream, we're going to have a different reading for the natural amount of oxygen that's at equilibrium in the water at a high altitude than we are in the ocean at sea level. Okay, so that relationship of pressure with altitude is pressure at a certain height, pH or P altitude, equals the initial pressure at sea level minus this constant, so that's for different temperatures that will change, but this is at 25 degrees Celsius, and times the height that you're at, the altitude you're at, h, in meters above sea level. So at a certain height, it's 1 atmosphere, right? That's the pressure at sea level minus this 1.15 times 10 to the -4th times h. All right, so at sea level, that's just going to be 1 atmosphere. So that's pretty clear. But if we increase our altitude, then we have a different story. Then at 1,000 meters, it's 1 atmosphere minus 1.15 times 10 to the -4th times 1,000 meters, or 0.885 atmosphere. Okay, so let's continue then. For oxygen, let's look at this problem for oxygen. If we're at 1,000 meters, the pressure of oxygen at 1,000 meters equals the percent of that gas in the atmosphere. So we need to know the concentration of the gas in the atmosphere times this, the pressure that it would be at that particular elevation. Okay, so for the pressure, at 1,000 meters, we already solved is 0.885 atmospheres. 21% of the air is oxygen, right? And so it's 0.21 times 0.885, which gives us 0.186 atmospheres. So that's at 1,000 meters. That's only for oxygen. Now, we can go to our Henry's law and solve for the amount of oxygen that's going to be in equilibrium, that's going to be dissolved in water at 1,000 meters. So that's our Henry's gas constant times the partial pressure of oxygen at 1,000 meters. So that is 0.186. We just solved for that. The concentration, that's what we're looking for. This is our Henry's gas constant specific to oxygen at 25 degrees Celsius. All right, and so we find that the concentration in moles per liter is this 2.34 times 10 to the -4th. We can solve to put that into milligrams per liter dissolved in water. So if we multiply by the molecular weight of 32 grams per mole and then convert to milligrams, we end up with the concentration of oxygen in water at 1,000 meter above sea level, 25 degrees Celsius, is 7.5 milligrams per liter. Okay, so at sea level, is that higher or lower? Think about that. At sea level, is that going to be higher or lower? Lower. At sea level, if we come back, this pressure is not 0.885, it's 1, right? Because it's just atmospheric pressure, sea level 1. So then that means this is 0.21, all right? And then we would be able to just continue through. All right, so we can figure that out for different altitudes just based on the pressure and altitude relationship.